Hello, my name is Barış Aşkın. My group friends for EEE475 course project are Mehmet, Emin, Öztürk, and Yavuz Yarıcı. Our project topic is Convex optimization approaches to linear system of equations in magnetic particle imaging. First, I want to briefly mention about magnetic particle imaging, or MPI in short, and system model for calibration-based reconstruction. MPI is a recent non-invasive imaging modality which provides high spatiotemporal resolution. It's a promising imaging technique for future clinical applications, including cell tracking and angiography. The most common image reconstruction method in MPI is called calibration-based reconstruction, and it uses this classical linear forward model. S times C with some noise is equal to U. Here, S is a system matrix modeling the scanner, and it is measured with scanner calibration. C is unknown image vector, N is noise, and U is measurement. For measurement vector and each column of system matrix, we first take Fourier transform of real-valued time domain signal, delete one conjugate symmetric part, and concatenate real and imaginary parts row-wise. To reconstruct an MPI image, we need to solve this optimization problem. Here, we minimize image regularizers with data fidelity term which provides consistency with system matrix and measurement. In this project, we implemented three popular convex optimization problem solver: Kajmars, as known as algebraic reconstruction technique, fast iterative shrinkage thresholding, in short FISTA, and alternating the direction method of multipliers, in short ADMM. We tried different regularization functions within these methods.
In the project, we use both 2D and 3D MPI data. For 2D, we use simulated system matrix and measurement signal produced in UMRAM with reference image given in homework 3. To avoid inverse crime, the high-resolution system matrix and reference image is used to generate the measurements. During reconstruction, we used much lower resolution system matrix to mimic a real scenario better. In addition to homework phantom, we generated 4 more simulated phantoms and retrospectively generated their measurements using low-resolution homework system matrix. We cannot avoid inverse crime since we do not have access to high-resolution system matrices for these phantoms. Before reconstruction, we applied row norm thresholding to system matrix with a threshold of 10% of maximum row norm. For quantitative results, we conducted experiments of noiseless, 10, 20 and 30 signal-to-noise ratio cases with 20 Monte Carlo iterations. For 3D, we used OpenMPI dataset, which is a public dataset consisting of several system matrices and measurement data. We reconstructed their resolution phantom with all methods. However, since we do not have an access to ground truth for experimental data, we compared the results only based on our visual evaluation. For system preprocessing, we project the system matrix and measurement data on the first 2,200 rows of U matrix in SVD decomposition of original system matrix. Our first method is Kajmars. Kajmars is an LSE solver by projecting the solution onto the solution set of each row equation iteratively, which is commonly used in MPI literature. In previous studies, solving this minimization problem means enforcing energy sparsity of image with data fidelity term. In our implementation, we selected row equations in randomized order in each iteration. We implemented 2 versions of Kajmars. First, we solved the standard system S times C equals to U for C with Kajmars iterations. Secondly, we implemented regularized Kajmars by extending the system with weighted identity matrix and introducing new unknowns for residual errors to handle inconsistency. We selected regularization parameter of a number of iterations by looking at PSNR and SSIM scores of homework phantom reconstruction. You can see iterations of Kajmars and regularized Kajmars iterations within a sample reconstruction. FISTA is a type of an iterative shrinkage thresholding algorithm based on general forward, backward splitting methodology to solve convex optimization problems. In MPI studies, FISTA method enforcing the sparsity in wavelet domain is proposed before, and in our implementation we used 2 versions of FISTA. We used a one-norm minimization prior or total variation minimization prior. For proximal operators, we use soft thresholding for Vista L1 and Chamboulet projections for Vista total variation. We selected step sizes and number of iterations by looking at PSNR and SSIM scores of homework phantom reconstruction. You can see animations of Vista L1 and Vista total variation iterations within a sample reconstruction.
ADMM is a powerful framework for convex optimization problems. It uses variable splitting, and this enables algorithm to introduce as many regularizers in the problem as desired. Previously, ADMM-based method is used for MPI image reconstruction in the literature. They solved the problem minimizing total variation and L1 norm of the image subject to the data fidelity with a noise limit. In our implementation, we use 3 versions of ADMM, in which we enforce only L1, only TV, or both L1 and TV sparsity. For L1 subproblem, we use soft thresholding. For TV subproblem, we use Chamboulet projections as proximal operators. We selected proximal operator step sizes and number of iterations by looking at the PSNR and SSIM scores of homework phantom. Epsilon value is found by using the additional noise level for simulated data and by trial and error for open MPI data. Here, you can see animations of ADMM L1 and TV, ADMM TV, and ADMM L1 iterations within a sample reconstruction.
We have 5 simulated phantoms: homework phantom, simulated phantom 1, 2, 3, and 4 with known ground truth. We conduct the experiment under 4 different noise settings. We reported PSNR and SSIM scores of each method, average on 20 Monte Carlo runs. In each run, all methods reconstruct with the same noise realization for fair comparison. The IQS scores of simulated phantom 1 can be seen in the table. From the results, one can see that Vista and ADMM outperforms Kajmer method in general. However, the performance of the Kajmer method does not change too much with the noise level. The best results are obtained with the ADMM L1 and TV for noiseless image. As the noise decreases, the performance of the ADMM methods significantly decreases. Hence, the most noise-sensitive methods are ADMM methods. For 3D analysis, we use same methods. In our experiment, we use OpenMPI simulated matrix and measurement data for their resolution phantom. The photograph of the phantom can be seen in the figure. To compare results based on our visual evaluations, we consider the original phantom photograph and the middle slice of the reconstructed phantoms. We can see middle slices for each reconstruction in the figure. It can be said that using a regularization of its paper and cell type artifacts on the reconstructed image, comparing Kajmers and regularized Kajmers. Although both Vista TV and Vista L1 could reconstruct the main phantom structure very well, using L1 norm prior yields very clean background compared to TV. And the best reconstruction quality is obtained with ADMM L1 and TV and Vista L1 based on our visual evaluations. We analyzed and compared the performance of selected methods. We made comprehensive quantitative and qualitative analysis of all methods with different time regularizers, using different phantoms under different noise settings. Our general observation is that ADMM L1 and TV and both Vista methods yield best reconstruction. As the scenario decreases, Vista outperforms others. And unexpected results obtained during test. Our expectation was that ADMM L1 yields better reconstruction results. However, it fails to capture even main phantom structure, especially under high noise. The CPU runtimes for each method can be seen in the table. The fastest method is Kajmers, and the slowest method is ADMM L1 and TV in terms of CPU runtime. It is mainly because Kajmers method requires very few iterations, while the ADMM requires much more iterations. To improve results, one possible way might be to use better system matrix. The condition number of the system depends on the singular variance distribution of the system matrix, and it affects the solutions. If we can collect better system matrix with close and high singular values in our MPI scanner, we would get better reconstruction. Here is our references.